Chapter 2 begins with the trigonometric functions of acute angles. Like I said, this might be closer to the trig you remember from geometry class, with the definitions you remember from geometry class. So let's first start talking about the right triangle based definitions of the sides and angles for any right triangle. It's pretty obvious, and I do want you to draw two of these. Which one of these is the right angle? It's this one. Great. So we're going to put the symbol for a right angle in that corner. Do y'all remember that symbol? Indicating a right angle. Now, I want you right now to put an angle as your reference angle as this lower guy, so that we're looking at what's called eventually an angle of elevation. And let's define the legs and hypotenuse of this triangle in regards to that angle theta. Across from theta, we would call that the opposite side. And I'm just going to write OPP. Is that okay for everybody to know that means opposite? Great. That is the side opposite of theta. The side that is touching theta would be called the adjacent side. The adjacent side. And our longest side that's always across from the 90-degree angle would be called our hypotenuse. Are we cool with all those shorthands for those sides? Yeah. Great. Now that's pretty obvious. We get this one. That's great. But what if our reference angle wasn't the one that looked like an angle of elevation? What if it was this up angle? How would that change our definition of the sides of the triangle? Well, we still have our right angle. We would still have our hypotenuse. But what would happen with the label I gave to the other two legs? Would they stay the same, labeled opposite and adjacent? No, because I changed the reference angle. Now this one flat down there is the one that is opposite to our angle theta. And the one that goes up and down is the adjacent side. And the reason I wanted you to draw both triangles and label the different sides is because we're going to be referencing not just always the typical angle, which is the angle of elevation, which is how we defined all of our trig functions in chapter 1 with a y value, an up and down value, and an x value, a side to side value. But we might be referencing an angle up at the top of our triangle. So we need to make sure we know that. Does anyone remember the acronym you probably learned in geometry class that gives you the ratios for sine, cosine, and tangent in regards to these words?
SOHCAHTOA.
SOHCAHTOA. Let's write that one down. So for sine, that is so. For cosine, that is ka. And for tangent, that is the toa. SOHCAHTOA. Maybe put the little cloud emphasis on our notes. Because really, if you remember SOHCAHTOA, and you remember which functions are reciprocals of which, you might not even need to write down what's in this next box, because SOHCAHTOA tells you everything. I would write it down because it's our notes, but if you can remember SOHCAHTOA, you got it all. For sine of theta, which we defined in the last chapter to be y over r, we can now call that the opposite over the hypotenuse. That's specifically for that first triangle we wrote that looked like our reference triangles in the different quadrants. For cosine, since it's ka, that would be the adjacent over the hypotenuse. And since tangent is toa, y over x, it is the opposite over the adjacent. Do these definitions sound like something you learned in geometry class? Kayla, you better say yes since you had me as geometry teacher. So we have these definitions that are now putting our definitions not in coordinate points and a radius, but as sides of a right triangle. If we know SOHCAHTOA, we can then find all of the reciprocal values, which means that cosecant would now be defined to be the hypotenuse over the opposite. That is just the reciprocal of sine. Secant would be defined to be the hypotenuse over the adjacent, the reciprocal of cosine. And cotangent would be the adjacent over the opposite, which is the reciprocal of tangent. So again, we have all of these definitions, but if you can remember SOHCAHTOA, you got it all. let's just practice to make sure that we understand these different ratios. So for this first triangle, which I would recommend putting, example 1 and draw your triangle, we're going to find sine, cosine, and tangent for both angles A and angle B in the figure. So if I start laying those out, and I'm going to find the sine of angle A, I need to make sure when I'm putting my ratios together, I'm actually looking at the opposite and the hypotenuse. So looking at this triangle, what side length is opposite of A? 7. So this is going to be 7 divided by the hypotenuse, which is 25. So opposite over hypotenuse. If I'm setting up the cosine of A, again, making sure I'm looking at the angle A, what is adjacent to angle A? 24, and the hypotenuse was 25. Now I'm doing the tangent of A, so I'm on to SOHCAHTOA, opposite over adjacent. What is opposite of A again? 7. And what is adjacent to A? 24. But this question also wants me to find sine, cosine, and tangent for angle B. So now we're going to change the angle within this triangle that we're using as our reference. And if we go back and find the sine of angle B, it changes what is opposite and adjacent. What is now opposite of B? 24. And what is the hypotenuse? Well, that part didn't change. Still 25. The cosine of angle B would be the side adjacent to B, which is the side length of 7 over the hypotenuse, which is 25. And tangent of angle B, I'm taking the opposite, 24, over the adjacent, 7. Because I notice that the cosine of A is the same value as the sine of B, and A and B in this triangle, what would they have to add up to if we had their angle measures? If all triangle is 180, this is 90, what do these have to add up to? 90. That means that there's some relationship amongst these angles in regards to this 90-degree right triangle. Again, I noticed that sine of A and cosine of B are the same. That's some relationship between A and B. We know they are complementary angles. And then, of course, the tangents are going to be reciprocals of each other because we've just changed which one is opposite and which one is adjacent. But that leads me into the next term that we're going to be using in this class, which is called a cofunction. For any acute angle A, the same exact thing you just noticed, that sine and cosine go together except that they're different angles, and those angles have to be complementary, allows me to say that they are cofunctions with each other. So sine and cosine are cofunctions, which means secant and cosecant are cofunctions, which means tangent and cotangent are cofunctions. So again, this follows from what we just did on that other paper, because we noticed that the values were the same if the angles are complements of each other. They would add up to 90 degrees. So we can write functions in terms of their cofunction by recognizing that they're just complements of each other. If we're going to write each of the functions in terms of its cofunction, first thing is to remember which one it's a cofunction with. So cosine goes with which one as a cofunction? Sine. So the things that I would know is the following equation. I would know that the cosine of 52 degrees should be equal to the sine of 90 degrees minus that same angle from the cosine function. So whatever angle is within cosine is what you're subtracting from 90, because they're complementary angles, and we saw that on the other side. So I could say that sine of 90 minus 52, well, that's 38 degrees. So cosine of 52 degrees would be the exact same as sine of 38 degrees. And if we found their ratios, we got their ratios out of a calculator, they should be exactly equal. The same way they were equal in that example before lunch. Make sense? So if I'm looking at tangent of 71 degrees, we remember what is the cofunction with tangent. Which one is it? Tangent is with cotangent. So tangent of 71 degrees would be equal to the cotangent of 90 degrees minus that same angle 71 degrees. So then we just do that quick subtraction problem. So tangent of 71 degrees is the same as asking the cotangent of 19 degrees. Easy? Just one more to make sure we got it. We're asking you to write secant of 24 degrees in terms of its cofunction. Secant is a cofunction with, what's that one called? Cosecant. So we do cosecant of 90 degrees minus the angle 24 degrees. Then we just have to do 90 minus 24, which is 66 degrees. Now later on in this chapter, we'll talk about how to more appropriately use the calculator. One of them is pretty easy, but we also want to be able to approximate real or exact values for values of the special right triangles. There are two special right triangles. One of them is called a 45-45-90 triangle, and one of them is called a 30-60-90 triangle. Do these look familiar to you? Yeah, there's a pattern or ratio amongst their side lengths where across from the 45-degree angles is x, and across from the 90 degrees is x times square root of 2. But in geometry class, you probably learned this pattern with this little tic-tac-toe chart. And if you didn't, you're going to learn it now. The pattern with 45-45-90, remember, across from 45 is x. And for us, what I would like for us to do is allow x to be 1. So if I called this 1, 1, this would be square root of 2. Because 1 times square root of 2 is just square root of 2. But a lot of times, and if you can think back, if you've taken pre-cal or AP pre-cal, to the unit circle, the radius of the unit circle, which would be the length of the hypotenuse of these triangles, was always 1. What did I do to divide square root of 2? Wow, I just gave away the answer. I divided square root of 2 by square root of 2 to make it 1. Let me write, don't write this down, just watch. Square root of 2 over square root of 2, doesn't that cancel out and make 1? So I divided square root of 2 by square root of 2, which means I need to come in here and I need to divide 1 by square root of 2 as well. Now, hopefully some of you guys have your spidey senses going off. Are you allowed to leave square roots in the bottom? No, so how would I rewrite this so that the square root is not in the bottom? Square root of 2 over 2. Those of you who've taken AP Pre-Cal, are things looking familiar here? From your unit circle? They should be. In a 30, 60, 90 triangle, there is also a special relationship amongst the side lengths. They make a particular ratio. In geometry class, you probably set up this tic-tac-toe board, 30 degrees, 60 degrees, 90 degrees. And if we look at our special right triangle on our page, across from the 30 is x, so we're going to call that 1. Across from the 60 is x square root 3, so we're going to call that 1 times square root 3, which is square root 3. And across from the 90, it says 2x, so 2 times 1 is 2. But again, we want this to be written where the 90-degree angle is our unit circle with a radius of 1. So what did I do to make 2 into 1? divided by 2. So I'm going to divide the rest of these by 2. Since for each of these tic-tac-toe boards, I was looking at the side opposite from the angle, opposite of the angle, I was actually finding all of the values of sine for these angle measurements. So we can use these patterns in these special right triangles, and I went over the pattern itself because we have a few people who will still take the SAT this semester. These patterns are things we need to remember for the SAT. They've shown up before. To be able to find the 6 trig values for a 60-degree angle, but we're giving an exact answer. So we can't plug this one into a calculator. The calculator would give us a rounded answer. In fact, these are irrational numbers, so the calculator would never be able to make it into a cute little fraction. But we have found all of the sine values for these particular functions, which means the sine of 60 degrees, if I look at my chart, since I was looking on the opposite side of that triangle, is square root of 3 over 2. In the idea of cofunctions, cosine of 60 degrees would be the same as the sine of what angle? Sine of 30, because 90 degrees minus that angle 60 degrees means that this is the sine of 30 degrees. And what does my little table up there say the sine of 30 degrees is? 1/2. Tangent of 60 degrees would be opposite of 60 degrees, which is square root of 3, over adjacent to 60 degrees, which is the 1. So that means the tangent of 60 degrees is square root 3. So in this one problem, use the tic-tac-toe board. I used cofunctions and I used SOHCAHTOA, which means we can go back and forth between the different ways to represent trigonometry and trigonometric ratios to get these values. Now, if we're wanting to do the reciprocals, because it asks for all 6, sine and cosecant are reciprocals. So if I'm doing the cosecant of 60 degrees, I would just flip that fraction over. Yeah, what's up?
For the cosine of 60, why did we use 1/2 and not 1 in the chart?
Cosine of 60, what do you mean?
Well, the second problem was cosine of 60 degrees is equal to sine of 90 minus 60. And then you use 1/2 for the answer. And then the next one we did square root of 3 and not square root of 3 over 2. Would it matter?
Okay, so because this table is just telling me sine, because of the way that we built it. Across from, or opposite of 30 is the 1. Opposite of 60 is the square root of 3. Opposite of 90 is the 2. So since I'm looking at all of the opposites, I'm looking at sine, because I divided by the hypotenuse. So it's opposite over hypotenuse. That's the sine of these functions. So this table right here is not telling me the value of sine, cosine, and tangent for these different angles. This is only sine. Good question. If we're flipping over that fraction, we'd end up with 2 over square root 3. I know you know we can't leave it like that. How do we write this answer? I hear this. That's it? Over 3. Okay, good.
I had that down. I just didn't know if that was right.
Girl, speak your mind. That was right. If we're doing the secant of 60 degrees, which is the reciprocal of cosine, it's 2 over 1, which we can just write as 2. And if we're doing the cotangent of 60 degrees, we got 1 over square root 3, and we would rationalize it to what? Square root of 3 over 3. Now, I know some of us know more trig than this, and I think, Troy, the reason why you're asking your question is because we're used to a different table when it comes to these trig values, especially if you've taken AP Pre-Cal. Do y'all know the table I'm talking about? It's the table you had to answer on all your formula quizzes for me every day in class.
I forgot it.
Oh no. Well, I have the table for you because I'm going to have you know the exact values for different angles. And instead of having to go through all this business to think about the cofunction and think about opposite over adjacent each time, for the exact values, we can reference this table in this class. If you have it memorized, that would be even better. The main point I'm trying to make here is if it says give an exact answer, which is what this problem says right here, the words exact answer mean that I can't turn to a calculator to answer the question. I need to either use my table, the unit circle, the hand trick, some of the other ways that you know your trig functions for these special right triangles. Otherwise, throw it into a calculator, which we will get to later in this unit.